Welcome to module 9, lecture 2. So, in the last lecture, we looked into high strength concrete, some properties, we had introduction, principles, etc., and some properties. Today, we look into some more properties and then basic issues, some tests that we do for workability and related possible mixed design scenario, mixed proportioning scenario, and then self compacting concrete we will just introduce today. So, that is outline of our discussion today is HSC high strength concrete properties, MDF macro defect free matrices, because other high strength matrices we will look into today, and then DSP densified with small particle, and reactive powder concrete, and just introduction to self compacting concrete. So, some of these we will look into today. So, if you recall in the last class we just said that high strength concrete has got high modulus of elasticity and low fracture toughness, because area under the curve is low, all right. And then it has got very good durability by and large, most of the cases it has got very good durability, it has got improved mechanical properties, most of it, and then fraction energy, then stress intensity factor, they are better, but not proportionally better, and CF, these are the micro cracked zone, dimensions of micro cracked zone ahead of tip of advancing crack, these are again fracture mechanics related properties, these are smaller than the normal concrete. Fire property is of course suspect, that is where we stopped in the last class, and then let us look into other properties such as creep. Now, creep of high strength concrete, both in terms of creep coefficient or specific creep. If you recall, when we discussed about creep, we defined creep coefficient as well as specific creep, both specific creep both, and both are actually significantly lower than normal strength concrete. So, it is significantly lower than normal strength concrete, significantly lower than normal strength concrete. Now, as we have discussed earlier also, that actually creep is relatively less understood, its mechanism is relatively less understood. Here also seems to be there is a limitation of information and also limitation of understanding. So, but what we understand is creep is lower. So, normal strength concrete significantly lower, but we have somewhat better understanding of shrinkage, and that is what we have seen earlier also. When we talked about shrinkage in general, the drying shrinkage, amongst there we classified the shrinkage in various classes, chemical shrinkage, autogeneous shrinkage, drying shrinkage, we classified them, all of them, plastic shrinkage and drying shrinkage, all we classified. Drying shrinkage is lower because of lower vapor permeability than normal concrete, because this is lower. So, vapor cannot get out, because a dense structure, dense microstructure, low capillary porosity, less water cement ratio, therefore, vapor permeability is lower. So, it does not get dried so easily, vapor does not move out of the system. So, therefore, it has got better drying shrinkage properties, it is lower, drying shrinkage is lower. So, creep is lower, drying shrinkage is also lower. So, this is an advantage in terms of usage, right. But this is not same with autogeneous shrinkage, because this is higher, autogeneous shrinkage is higher, as you can remember, it is higher, because this has nothing to do with the loss of water. If you recall, if you remember, we discussed that this is the shrinkage that occurs in sealed specimen, this occurs in sealed specimen, and largely related to when you have a sealed specimen, there is no drying, nothing is going out. Chemical shrinkage was related to volume changes, right. Chemical shrinkage was related to stoichiometric volume changes. Autogeneous shrinkage is related to, in a sealed specimen, shrinkage do occur, all right. There is no drying, nothing is going out, but because of the self desiccation process, water is lost in the system, and this water loss causes some kind of system shrinkage, because there is empty pores with dry empty pores will be there, and which means that in the gel will lose some water into those new pores, or that would be empty pores that is there, and as a result there would be shrinkage. So, this is very much there. Now, this is related to production of more quantity of CHS gel, because more you produce CHS gel and other hydration product, more of the water will be consumed. So, low water cement ratio, anyway your space is less, it is a dense structure, but hydration products would be forming more CHS gel will be forming silica fume reacting with calcium hydroxide, it also would form more CHS gel, and water is consumed in all the hydration process, it all occurs in the presence of water, and therefore, this leads to more self desiccation and subsequent internal non availability of water in the pores, leading to shrinkage. So, autogeneous shrinkage is more, and this is of course, a concern in case of high strength concrete. Like I said, fire properties are a concern, autogeneous shrinkage is also a concern. So, more rapid, and it is also more rapid than the normal strength concrete. So, during the time during which your normal strength concrete will, let us say, show 40 microstone strength, say normal strength concrete might show normal strength concrete may exhibit 40 microstrain. Same time high strength concrete may show 100 microstrain. So, at a given time microstrain, right. So, at a given time, so it is much faster also. So, not only it is more, it can be faster also. So, therefore, this is surely one aspect one must look into, right, one must look into in case of high strength concrete. Of course, it has got implication in the design, and therefore, it could design implication could be quite prominent. Now, you must understand the high strength concrete would be used, you do not use them in all structures. High performance concrete, you may not use them in all structures. All right. In last class, we seen that it has got better durability. All right. So, you might be using simply high strength concrete or high performance concrete from the durability point of view, because it is a dense structure, So, the places where this is likely to be used are tall buildings, long span bridges or in extreme severe condition, and there those structure, tall structure, we know that shrinkage has got a kind of importance in taller structure. For example, Petronas Tower in Kuala Lumpur was also in high strength concrete. The Bombay Bandra Orly link, it uses high performance concrete, and some of the flyovers in Mumbai, JJ hospital flyover, I think it is that is one of the flyovers, they have used a high strength concrete 70 MPa, 75 MPa, 90 MPa and so on, or 100 MPa concrete. Now, they are being used in such structures where it may be worthwhile to use them, or for that matter the airport terminal, new airport terminal in Chennai is using 60 MPa plus M60 grade concrete or something of that kind. Now, these are the structures where you are using them, and some of those long span bridge which are pre-stressed, the shrinkage could be an issue. Therefore, one has to think about their implication in design, or tall buildings, as we said, they could be they might have their implication in design as well. So, one must look into this. So, therefore, this is important, but drying shrinkage is lower, as we have already said. This is because of lower vapor permeability than normal strength concrete. So, drying shrinkage is lower, autogeneous shrinkage is higher, that is because of this no water can get out of it. So, therefore, drying shrinkage is generally lower for low vapor permeability, but autogeneous shrinkage is higher. If you are the mixes that you should be doing, that should look into the packing density and appropriate paste. Now, while talking about mix proportioning earlier, we said that you remember we talked about packing density of aggregate system. So, you look into the packing density of aggregate system and then put appropriate paste quantity, aggregate packing through experiment better and binary ternary mixture to determine the paste content required. You can follow it up to assume that there will be fully dispersed paste, it will be fully dispersed paste. So, paste 15 to 20% higher, right, for silica fume 10 to, and silica fume generally is 10 to 15%, not 15%, could be 10% is a good amount. So, 15 to, so you have actually 1 minus packing density, actually 1 minus packing density, I do not remember what I used, but just let me put it 1 minus packing density gives you whatever value you give, multiply this by about or plus 10 to 15% extra paste, extra mortar, extra paste, here to add paste. So, paste here in higher strength concrete could be somewhat higher, and silica fume content is this. In very high strength matrices this is higher. So, just see that it is workable. To make it workable, paste content would govern the workability as we have discussed earlier. So, it might be 10-15% or even less depending upon what is the kind of workability one desires. So, you can determine the paste content and by packing density. For water to cement silica water cementitious ratio, what we are saying cement plus silica fume, because largely it is silica fume which is used in high strength concrete, varying between 0.2 to 2.5. FC, that is 28 days compressive strength, might be 110 for moist cured situation, that is and 125 to 130 if it is water to water cementitious ratio being 0.15, steam cured or heat cured, and this can result in economy of the section and viable. Dimensions could be smaller. So, you see you can use about somewhat higher amount of paste. So, obviously, the cost will increase, cement, silica fume, everything is going up, but remember here the volume, the mass basis silica fume content, total cementitious material may not increase significantly, because silica fume is highly reactive and its pozzolenicity is quite high. So, paste 15 to 20% higher could be there depending upon the workability requirement. Silica fume as a percentage of total cementitious should be around 10%, maximum 15%. Water to cement ratio 0.2 to 0.25, we will get around 110 MPa concrete, that is generally the range, but one has to design this material, and you can have moist cured. But if it is heat cured, you can go to slightly higher lower water cement ratio and get a strength of 125, 130, right, and dimension of the section will reduce, and therefore, and if you are pre-stressing it, you can imagine you will get 120 MPa concrete and you are pre-stressing it, it can dimension could be significantly low and economy can be achieved, even though the cost of the material will be higher and it could be a viable situation. And in tall or long span bridges, maybe this is a requirement, very longer span. Earlier we could go with the M45 grade of concrete in the deck, pre-stressing 45-50. If we are doing pre-stressing, we could have got to about 120 meter span of pre-stressed concrete bridges. Well, this high strength concrete you might even go to longer span, box girder segmental construction, you can actually go to about 120 meters, somewhere around in 1970s. The bridges those who are constructed with M45-50 grade of concrete, pre-stressed concrete, box girder, double cantilever construction, maybe suspended span or centrally hinged later on. They could go to 120 meter spans, but this could be much higher, 150 meter span and so on and so forth, and very high strength system might even take you to 200 mm, 200 meter, like reactive powder concrete can take you to 200 meter spans of the bridges. Bridge decks can be also of high strength concrete and so on, high performance concrete. So, there one might use this and this might be economically viable. I have already mentioned the places where they have been used. Now, just before that let us look into this. This is very important component. One is the packing density issue. Determine the packing density of all your aggregate system. If you want to optimize your paste content and the cost therefore. And the superplasticizer compatibility is another issue. One of the tests used by a lot of people is the Marsh Cone test, originally meant for the mining engineers. They use for I think crude oil to find out their flowability. So, Marsh Cone looks like this, and you fill this material in a given way, 1.2 liter capacity, fill it in a given way, dimensions are something of this kind, and then time required to empty this was found out, or time flow for certain period of time you can find out. The other it will look like this. So, in this axis you can say time of flow for certain quantity of the material, fixed quantity of the material, or complete emptying becomes difficult. So, you might do it in the paste, and dosage of superplasticizer you can change, and you can see the time of flow reduces as you increase your superplasticizer dosage. So, if the time is low, it means flow is better, and for different superplasticizer you might get this kind of values, might choose a suitable superplasticizer based on this, and then optimal superplasticizer content for different silica fume content 0, 5, 10, 15% has been plotted here. All right. So, you can see that optimum superplasticizer content is somewhere for the best for the water cement ratio of cementitious ratio of about 0.35 is somewhere here. So, for various water to cementitious ratio, as you go on increasing, you do not have to increase the optimum superplasticizer dosage remains same. So, you can find out the combination or optimum superplasticizer that you require for the best most compatible superplasticizer that you determine from here through Marsh Cone test. You can actually determine, I am not going to detail into this, but actually using Marsh Cone test actually you can find out which is the best superplasticizer and what is its optimal dosage. Similarly, you can use slump cone test, mini slump test. We talked about mini slump test earlier. Same mini slump test you can use. We just talked about this earlier. Mini slump we can do, and compatibility you can determine depending upon different time after just mixing. If you determine the slump flow with time, for a given water, usually people have been doing for water cement ratio of 0.35 and at 20 degrees centigrade, and if this is actually reducing down, that is the flow, total quantity of flow in millimeter, the spread in millimeter, if it reduces with time, then this is not compatible, but if it remains constant for certain period of time, then it is actually compatible. So, details I am not discussing. Using mini slump test you can find out compatibility, and also using Marsh Cone test you can find out the best, most compatible, most suitable superplasticizer with your paste, and then find out the optimal dosage for each percentage of silica fume and water cement ratio, water cementitious ratio you are dealing with, and use that actually. So, selection of superplasticizer is very important. So, that was related to high strength concrete and high performance concrete. Now, where they have found their use, high performance concrete, HPC or HSC, as I told you, examples are Petronas Tower, all the tall buildings these days, tallest building these days, many of them are using actually HSC. In India, I told you Bandra Worli Link, Sea-Link, many flyovers and buildings in Mumbai, they have used greater than more than M60 concrete. Airport, new airport terminal building in Chennai, that also part of it used M60 grade of concrete. It is the signature bridge, tower bridge in Delhi, maybe it is also using some part of it is high strength concrete. So, many places this is M60 grade concretes etc. are using worldwide. This has become quite popular and useful material. So, with that we of course finish our discussion on high strength concrete. We can now look into the other high strength matrices, and one of them is macro defect free cement. Now, what is it? Water soluble polymer. As I told you, you can apply a high pressure, you can apply high pressure onto the paste, you can apply high pressure onto your paste, high pressure onto your paste, you can apply high pressure onto your paste, high pressure onto your paste. Okay, it is a piston, let us say, and apply high pressure onto the paste which is there, high pressure onto the paste which is there, and as you apply high pressure onto the paste, you can increase the strength. Now, supposing I do not, it is very high pressure and I do not want to employ that kind of high pressure, wanted to employ some kind of lower pressure, then it has been observed that material like this high alumina cement, polyvinyl alcohol, and if you apply some pressure, these are basically, this is PBA is water soluble polymer and some form of cement, and apply some pressure and 5 MPa at 80 degree centigrade, let us say 5 MPa pressure at 80 degree centigrade, 5 MPa pressure at 80 degree centigrade for 10 minutes, and then give warm treatment at 80 degree centigrade for 24 hours, and result is a very strong material. So, strength could be, compressive strength could be as good as 400 MPa and its modulus of elasticity could be 40 to 50 GPa. So, this is macro defect free cement, all right. So, this is another high strength matrix, but this is of course kind of not readily available, it is a factory produced system and been used for electronic substrate, ceramics and such places. So, this is a high strength matrix, very high strength matrix you can see, and this you can, this is one, the other one is a densified with small particle DSP, and this is also cement ultrafine particle and use a kind of effective particle dispersant, same thing 20 to 30% ultrafine material silica fume, 70% cement, and again give a vacuum treatment and vigorous vibration for dispersion. So, vacuum treatment and vigorous vibration for dispersion of this particulate system, and then you might do some high temperature curing after mixing, all right, with a very low water to cement ratio less than 0.3, then you can get a compressive strength of this cement as greater than 150 MPa. So, this is densified with small particle DSP cement, and you can get strength as good as 150 MPa or greater than 150 MPa. Now, this can be used together with aggregate or sand, coarse or fine aggregate, and you can make mortar out of this or concrete, and you can see the properties that you are likely to get. For example, MSA 16, maximum size of aggregate 16, granite aggregate, you can get a compressive strength of 125 MPa and modulus of elasticity, dynamic modulus of elasticity 68. You use same size of MSA, use another kind of aggregate diabase, you get 168 MPa with this dynamic modulus around 65. You remember dynamic modulus, we talked about dynamic modulus, we determine it through actually by by actually acoustic or mechanical waves, by impinging mechanical waves. Now, 10 mm MSA calcined bauxite aggregate type, the strength goes to 218 MPa with the modulus of elasticity going to 109 GPa. Still use finer one 4 mm aggregate, that means no large aggregate, coarse aggregate is missing, calcined bauxite, and strength is 268 MPa and 108 is a modulus of elasticity. So, you can see that you can go to fairly high strength, I mean quite high strength using this material when you are using aggregate, but MSA higher obviously gives you lower strength, stress concentration, non-uniformity, all that we talked about because of that. When you have finer and no coarse aggregate, strength is much higher. So, another kind of material which was developed originally in France and possibly quite promising of the similar sort of high strength matrices is reactive powder concrete. Now, followed from this, actually if I look at, okay, I will just come to reactive powder concrete in a minute, but where can I use this DSP? Can be used in flooring. High strength concrete, I forgot to tell you, higher the strength of concrete is, abrasion resistance is very good, that is what we have seen. So, your high strength concrete will have a very good abrasion resistance. So, you can use that in flooring. Now, you want still better abrasion resistance, DSP could serve you good. Safe nuclear entrapment, tooling and molding, overlay over existing concrete as repair material, overlay over existing concrete as a like a kind of not repaired protective material, protection material. So, it can give you good protection against thin layer, may give you good protection against external environment. So, this is where DSPs have been used, but then I was talking of reactive powder concrete. Reactive powder concrete, we have seen while just talking about DSP that if as I eliminate out the coarse aggregate, discontinuities vanishes and stress concentration, those effect actually vanishes and it becomes a uniform material, homogeneous material, uniform material throughout by and large. So, in this one coarse aggregate is completely eliminated and fine quartz sand or steel powder, maximum dimension 600 micron, 600 micron. So, even the finer, you are not using all fine aggregate sizes, not going to 4.75 mm. So, it is reduced down further from 4 mm I talked about to now 0.6 mm and improve this mechanical properties of the paste is improved, all right. Then reduction in the aggregate to matrix ratio, about 20% higher paste than that required for optimal packing of aggregate. Why is it so? To reduce down the shrinkage, because now it will shrink in bulk, as I told you, it will shrink in bulk. That means, it will change its size dimension in this manner. And if you had an aggregate inside, let us say if you had an aggregate inside, that will get compressed rather than any kind of stresses or cracks at the interface. So, this will not be there, this will simply this will not be there, this cracks will not be there, instead this will actually get compressed from all this direction because of bulk shrinkage. So, when you have higher paste content, so if you can, if I just look at it, normal concrete will have paste content around 30% or so, 28, 32, 32%. You come to pumpable concrete, you require more paste because of the flow characteristics, and we will talk about a concrete called self compacting concrete, which will also need more paste because of its flowability on its own. But from the strength point of view, like when you are looking at higher strength matrices, again paste content increases. That is largely because we want to bring in homogeneity in one thing and then get rid of the interfacial shrinkage that is there, because aggregates won't shrink, paste will shrink. But if the whole system is shrinking in bulk with a less quantity of aggregate inside, the interfacial discontinuity or flow or cracking, that would be relatively less right in the beginning before any load has been applied. So, use actually higher amount of paste than required for optimal packing. Now, you have to determine plastic property by thorough rheological analysis in this kind of material. So, that is this is how we get it. Reactive powder concrete, we enhance the homogeneity, enhance this homogeneity by elimination of coarse aggregate. The compacted density by optimization of granular mixture. So, you have to do a thorough packing density scenario, apply, but this is additional, apply pressure before and during setting. Now, this would ensure further compaction, and if you are going to a very high strength situation, this would be a requirement. Microstructure enhancement by post set heat treatment. So, you are actually doing all kind of conversion, everything should finish quickly. So, no microstructure is being enhanced by post set heat treatment. And if I want to increase the ductility of this material will be fully brittle, but as a material if I want to improve its ductility, I might put in steel fibers or some other fibers, particularly steel fibers would be useful, fine steel fiber, but the carbon fibers, graphene and such things could also be good, nanofibers for example, which are to be solved as yet, but steel fibers, fine microfibers, small size fibers can improve its ductility property of the material as a whole. Right. Now, this is one extremities of this one, it could be as low as 0.08 water to cementitious ratio, water to cementitious I will call it Cm rather than C alone, water to cementitious ratio Cm. Quartz aggregate has been used, powders have been fully dispersed, least agglomerated, and you apply a pressure of 50 MPa to reduce air bubbles, and you can maintain through out setting of 6 to 10 hours. Heat treatment after the concrete has set simply by ambient pressure, at ambient pressure, heat treatment at ambient pressure. So, this is what reactive powder concrete, and what you get something like this. There are two grades, RPC 200 grade and RPC 800 grade. So, RPC 200 grade no presetting pressure required, none, but 800 grade you need 850 MPa pressure, that is what I was talking about. Heat treatment 20 to 90 degree and 250 to 400 degree autoclave situation, maybe the heat treatment would be there. So, there is a pressure, and also you might do a heat treatment at higher temperature. Obviously, the name suggests 200 grade. So, 170 to 230 MPa. This one is 490 to 600 MPa using quartz, all right, if you are using quartz 0.6 mm down, and if it is steel balls or steel powders, then you can get as high a strength as 800 MPa or 810 MPa. So, that is why the grade name is 800, right, and flexural strength 30 to 60 for quartz and 45 to 141 for steel. Now, you see the potential of this material. 200 grade, first let us look at, if I get 175, 180 and pre-stress it. So, it is at least 150, 160 in tension as well as in compression. That is the kind of load it can carry. So, the section dimensions actually can be comparable to the steel sections and may turn out to be even cheaper in some situation, but remember it has to be precast. You cannot make it in situ, this has to be factory produced material. It has to be a factory produced material, and in fact, it has been shown some of the materials produced, for example, ductile is of the similar principle, its dimensions could be almost similar. For example, you have a steel section of this kind, I section, and you can have concrete section of the similar kind having concrete. This is concrete, this is steel, this is steel. Dimensions could be almost similar to take same kind of loads. So, you see this material has got an advantage, this material has got an advantage. Let us look at other properties. Fracture energy is low, because it should be, because no stress strain curve is almost vertical. Basically, it is very brittle material if you have not added fiber, and this is still lower, it is still lower per meter squared, joules per meter square, and ultimate elongation is low, here it is very small. So, there is hardly any elongation, it actually has a high modulus, relatively higher modulus, modulus of elasticity 50 to 60 GPa and 65 to 75 GPa. So, this material is potential, this material has got significant potential actually, and been attempted first I think in Canada in somewhere around 1990s. It is actually originally developed in France, but first pedestrian bridge was constructed in Canada somewhere around 1997, long span, and then also in Far East. Number of places actually some of this has been tried as a structural material, and commercial product like ductile, which is possibly based on similar principle produced by Lafarge, or there are similar other products by some other company, they are precast elements possibly are available, but this has to be factory produced totally in controlled condition, otherwise you can't produce this material. So, it has to be industrialized construction, but the material has got big advantage if you are looking for very long span or very tall buildings, there it will have a big advantage. The cost is also not it would be obviously higher than let us say high strength concrete and so on. But looking at everything put together, like by like comparison, if one does, perhaps many cases this material also may be viable. At the moment, of course, in Indian scenario, I have not come across a situation where RPC has been used, but it has got potential for very tall buildings and long span bridges and so on and so forth. So, this is reactive powder concrete, this is reactive powder concrete, right, this is reactive powder concrete, all right. So, last in our discussion today is self compacting concrete, which I will just introduce, and discuss a little bit today and discuss the rest of it in the next class. Self compacting concrete, how do I define? Well, it is the concrete that is able to flow and fill every part of the corner of the formwork, even in the presence of dense reinforcement, purely by means of own weight and without the need for any vibration and other type of compaction. So, it is actually it flows. Originally developed in Japan and Europe, basically to get rid of vibration for two reasons. One, the noise in a city, vibration creates a lot of noise, and therefore, you want to avoid that, there should be no noise. Second thing is there is a cost for vibration, and that cost can be eliminated, both labor, mainly labor cost and so on and so forth. So, that has to be eliminated. So, basically idea is that you put the concrete and it will flow. So, it will flow like this, you put the concrete into the any part of the structure and it will simply flow. So, something like this as it is shown. So, you have a slump cone test, slump cone, you have just lifted it and it will simply spread all around the places, it will flow in all direction. So, it will simply flow. So, therefore, flowability is the main concern of this one and it should be able to flow on its own. Now, how can concrete flow? We have looked into pumpability, and what we said was it can flow because only material that is flowable in such concrete is the water. Now, if I have sufficient water in the system and also some kind of dispersant. So, if you have some kind of disbursement, then it can if you want to put too much of water, because only thing that is flowable in concrete system is the water. But if you can't put too much of water, because that will not only increase the water to cementitious or water to cement ratio, segregation and similar many other things will occur. So, it should have a kind of cohesiveness, no internal separation, but at the same time it should be able to flow. So, it is actually the hyper plasticizer, third, fourth generation water reducing agent, very high or ultra high range water reducing agent, that made it possible. Actually for flow, to make self compacting concrete. Now, we talked of polycarboxylate ether. Remember, when we talked of admixtures, we talked of polycarboxylate ethers, which can disperse more because of their comb structure, push the particle by steric hindrances. It is that kind of admixtures which actually made it possible the production of self compacting concrete, because they can, if a normal quantity of water, they can push the particle apart and give a lot of flow, but at the same time particles should be retained together, they should not separate out. So, some stickiness should be there. So, some cases people use viscosity modifier, which we discussed again earlier, some sort of sticking property which they have, and therefore, both this admixture could make self compacting concrete possible. So, that is how actually it was developed in part of the Europe and Japan in the early days of its development in 1980s. Now, let us look at requirements of self compacting concrete. First of all, it must have filling ability, fill all corners through flow, all corners of the formwork flowability, ability to flow in the form without vibration, no vibration, I am not applying any vibration. So, it should flow in the form without vibration, and because when we talked of compaction, you remember the normal concrete will seldom attain the shape of the formwork. So, I need some mobility, and actually flow should be there, able to flow in the form, change its position in the form without vibration here. So, that time we were actually enforcing them or ensuring them through vibration, the mobility, getting the shape of the mold. So, there is some amount of movement. Now, here it should move on its own and actually attain the shape of the mold. It should be able to pass through narrow spaces such as rebar without blockage. So, if it is a self compacting concrete, must be able to pass through all reinforcement. So, passing ability. So, filling ability, flowability and passing ability. Filling ability means it should spread and actually fill the place, and then flowability means if required the space is there more you have put in. So, it should be able to flow and spread it, because you might put it in one place and it should fill all the portions. So, there is some flow is required. Passing ability, if there are reinforcement there, it should pass through those reinforcement and should have good segregation resistance during flowing and also after it has come to rest. So, no segregation after rest means water should not bleed out. While flowing, stones or the coarse aggregate should not remain somewhere, and the water or the paste should not flow away, leaving the coarse aggregates. So, therefore, there shouldn't be any kind of segregation or bleeding whatsoever before it has come to rest or during the flow. So, this is important. And how do you attain this? How do you attain this? I should have a consistent paste and it should be flowing. Paste itself should be showing. You can just advance a little bit from pumpable concrete, what we talked about earlier. So, pumpable concrete where you are putting pressures to move, self compacting concrete you should be easily able to pump, no problem at all, because we are not talking of slump anymore, 120 mm slump or 130 mm slump for the pumpable concrete. It is simply slump flow here, as I showed in a photograph earlier, and it should be flowable paste and consistent paste. Hence, hyperplasticizer use is must, that is what I said, and I must have excess paste higher than interstitial volume in aggregate at least by 10%, because as I said paste is the one which flows. I will just explain through a diagram later on this aspect more, and lesser coarse aggregate obviously will be the reason. You have high paste, less coarse aggregate, and then paste flows and carries the aggregate riding with it. Aggregate will have a piggyback ride on the paste itself, because they will be embedded in the paste, and that is how you can make it self compacting, because aggregates are unlikely to move or flow, not they are going to fill in spaces. They will have their angle of repose and hold it if they are alone, but it is the paste, if they are embedded in the paste and then paste moves, they should be also having a ride onto the paste and then move, and that is how it can be self compacting. Well, plastic on its own with appropriate viscosity, that means yield shear stress must be very little. I talked of yield shear stress long back when we were talking of pumpability, compaction and those issues, and we talked of Bingham's model if you recall. So, it should have it should be plastic on its own viscosity. So, basically you see if you look at it, this is your concrete, much less aggregate, aggregates are much less, this is your concrete, actually lot of paste, less aggregate. Now, if it starts flowing, whole thing flows, it is actually the paste which flows and they remain in their position. There should not be relative movement between this particle as it flows. So, you can imagine you have a viscous paste which flows and you have some number of aggregate, I am saying, just supposing it is a paste and you have made a paste with a hyperplasticizer and adequate amount of water in the hyperplasticizer, it is able to flow. Now, you embed some aggregates onto it, just push few aggregates onto it. Now, aggregate will also remain embedded in this position, and if the paste has got stickiness, it will remain embedded in this position and then move with the paste itself. So, whole system of the paste moves and therefore, embedded aggregate also moves with it. as if it is going to have it's having a ride onto the back of the paste. So, that is the idea, that is the idea, that is the whole principle. So, therefore, you must have less coarse aggregate content. Coarse aggregate content is less in this kind of a system, all right. Coarse aggregate content is less in this kind of system. So, as it flows, as it moves out and moves, but then relative position remains still same, it does not change. So, after movement it should retain this same thing, it should retain its cohesiveness. So, therefore, these are the two issues in self compacting concrete. The paste content should be higher. So, therefore, you have materials, of course, physical properties of the material, specific gravity, grading, etc., are important. Particle packing density is very important. You find out what is the particle packing density, and then because you are using different size aggregates, and then as you pack it, put lot of paste inside. I mean, put them inside, in a larger paste matrix, and which should be the paste matrix volume you can find out from the packing density. You might do that same Marsh Cone test to find out the super plasticizer dosage determination, optimal one, and fresh properties of self compacting concrete we measure by, not by conventional slump test, etc., but by slump flow spread, V funnel test, L box, U tube. We will discuss some of them, and this of course would be good if we can do it, but at the moment this is still in developmental stage. So, yield stress and plastic viscosity. So, if you see the proportion of the mix, that would be there. Water to powder ratio, you have sufficient quantity of water. So, volumetrically water to powder ratio is 0.8 to 1.1, right, volumetrically, not mass basis. Mass basis it will be obviously much lower, but volume of water must be sufficiently high. You can see if this is water has got a specific gravity of 1. So, multiply 1 by 1 divided by same, let us say pure cement, then it will be 1 divided by 3.15, but it will be some cement, some fly ash, because so much of paste quantity you need in this system that you can't have only cement. You will have to have some kind of filler material, large quantity, because paste quantity you want to increase. So, fly ash or something. So, you will have specific gravities depending upon the quantity of fly ash used. Let us say 75% point is fly ash, and 25% is 25% is fly ash, 2.2, and 75% is cement, right. So, you can have the volume, if 1:1, if this is equals to 1, water cement ratio will be this much. So, you will get a strength depending upon this water to cementitious ratio. Now, people ask whether is it possible to make high strength concrete as self compacting. Well, this should be possible, but it would depend upon the right kind of mix. Sufficiently high strength matrix, but very high strength and self compacting, well, that would be a real challenge. At the moment we are not talking of that kind of situation, we are only right now talking of self compacting scenario. So, the volume to powder to water to powder ratio, now that is why I am talking of powder, which might have been when not cementitious alone, not supplementary cementitious material, not SCM like fly ash, silica fume, etc., but we are talking of powder. Powder means even inert material, inert fine material. They should go into make, all this should make into paste, they should go into making of paste. So, they make paste. So, all that are required to paste. So, in the paste you have water to powder ratio is very important, because we have seen there is a water content which gives us consistency, all right, which is what we what we call the standard consistency is the water which will be just isolating the air bubbles, but you got to add more water here, because you want real flowability, right. So, therefore, the quantity of water to powder, that is very important. Now, all particles must be looked into. So, air bubbles are isolated plus more, because you want the flowability of the system. So, therefore, the water to powder ratio is the important issue, and total powder content might go to about 400 to 600 kg per cubic meter. The reason is very simple, because you want sufficient quantity of paste, that is what we have seen. So, you must want sufficient quantity of paste This is 28 to 35% of mixed volume. Now, if you look at normal concrete, supposing you have got about, you will have about 1100, 1200 or 1200 kg per meter cube of concrete, the volume of mass of aggregate, divide by 2.6, right. That is the volume of aggregate, 2.6 if you divide, and the concrete is 2400 kg per meter cube, divided by 2.4, let us say, specific gravity of the solid particle being something like this. So, you can find out this will be nearly 50%. In normal concrete, this will be nearly normal concrete, this is nearly 50%. Coarse aggregate content would be nearly 50%. In normal concrete, coarse aggregate content could be nearly very close to 50%, 45, 50%, but here it is 28 to 35%, because they got to have a piggyback ride on the paste or mortar. Coarse aggregate will have a ride on the mortar, mortar should flow, and they are sitting on top of the mortar, and they are just enjoying their journey and go to the right position. So, obviously, the mortar content will increase, mortar content will increase. So, obviously, the mortar content will increase, mortar content will increase, water content of course, around 200 kg per cubic meter, depending upon the water to cementitious ratio, but order should be of the similar. That means, what you are doing? You have not reduced in high strength concrete system, you reduce the water too much to get the strength, cementitious you keep saying. So, your water cementitious ratio is higher, lower to get the strength. Here you may not go for a strength at the moment. Supposing you are not interested in the strength, you can keep the water content high, but because you need water to powder ratio to certain level, but increase your powder content. So, paste content totally you increase depending, but ratio of this water to powder or water to cementitious system would govern the strength. So, water you do not reduce, but use still the plasticizer to make it flowable. In high strength concrete, you use the plasticizer to cut down onto the water. Here you are taking it to the full advantage of getting as much flow as possible. Fine aggregate content obviously will be higher, because normal concrete it will be around 700, and assume again 2.6 as the specific gravity. So, the volume would be this much and the content same. So, roughly around you find around maybe 30% is 30 volumetrically. Volumetrically this might be about less than 30, 20-25% in case of normal strength, normal flow aggregate or normal concrete, but here mass basis 40 to 55% of the total aggregate weight, much higher. So, in normal concrete will be 700 divided by, let us say, 1200. So, this is less than, this would be this this total aggregate content is actually here the sand content would be higher, because aggregate content is going out, overall volume of the aggregate system is lower, paste is higher, sand would be of this sort of sand would be of this sort of quantities. So, sand would be of this sort of quantities, sand would be of this sort of quantities, sand would be of this sort of quantities. So, that is how typically the fine aggregate, the proportions of the self compacting concrete. So, we just introduced the self compacting concrete in this discussion. So, we can actually look into the summary of this particular one here. Summary, you can look into what we have looked into. Summary, we have what we have looked into. Number 1, we looked some properties of high strength concrete. Then we have looked into some other very high strength matrices. Then we introduced ourselves to self compacting concrete. In the next class, we will look into self compacting concrete to start with, and if time permits, we will go to other concrete such as fiber reinforced concrete. So, with this I think we can conclude our discussion on this. What we have seen is, we have seen high strength concrete basically right from the beginning, what is the principle and the history. We also discussed a little bit of history of the self compacting concrete today and the other high strength matrices. So, and finally, we have come to the flowability, the high performance, one of the other kind of performance of the concrete, that is your flow properties or compaction properties, self compacting concrete, that is what we looked into. So, with this actually we would like to finish this discussion. Thank you.